तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome everybody to the lectures on computer graphics. Today we are going to discuss descriptions based on curves representation, and of course, it will be followed by the method on representing nonlinear surfaces, okay, or non-planar surfaces. Okay. We have seen in solid modeling the methods by which an object is defined by a set of polygons, triangles or quadrilaterals, and even for non-planar objects like spheres, cones, cylinders, let us say, which are considered as primitives in OpenGL. We know that you can use a sweep representation to construct the wireframe diagram, which represents a curved object using piecewise approximation. A small planar patch represents a small part of a curved object, but it is essential in certain applications that such piecewise approximation may not hold good. It does not provide you a very natural modeling of the surfaces which are curved, okay, or non-planar, I should say, where there are sharp bends either in 2D or in 3D surface, where there are large changes of curvatures of a surface, the gradient changes very fast. It is almost impossible to have a very good approximation using planar patches or using polygonal modeling. So, there is a need to represent non-planar objects with the help of curves in 2D and surfaces in 3D. We will look at curves to start with today, different forms of representing curves, which are not only used for modeling surfaces, but also could be used for drawing curves. For drawing curves, often you do not need to, often you of course could be joining points with the help of straight lines, but if the set of points which define the functional behavior of a system or an experimental data which you have observed, y is a function of x or z is a function of x y, 2D, 3D or higher dimension, it is in fact impossible to have a good representation of that curve or a surface in 3D or a curve in 2D with the help of linear interpolation. So, it is often necessary to obtain a curve, model that using a curve. The behavior of the functional form of the plot of the data present in the plot should be represented in the form of a curve. Okay, so, we look at the curve representation, and broadly I could say that the representation of a curve could be a non-parametric form or a parametric form. Y equals f x, I will say, is a non-parametric form, or a parametric form which I will say x of t or y of t t being the parameter. We know this parametric form of a line, which we have used for various applications such as clipping and intersections. Of course, we can have an explicit form in the form of y equal to mx plus b, or an implicit form of the form f x y equal to 0. This implicit form we already have used in cases where we use the Bressenham's algorithm, or also in the case of clipping as well. So, you can say an explicit and implicit form or a non-parametric parametric form. We will keep on interchanging between the two, but typically most of these curves representation follow the parametric form. We will see the parametric form is the most common representation of the curve, which is used in most of these cases. Okay, before we go on to discussions of various parametric forms, at least we know a few simple examples of curves representation. Let us say that take the equation of a circle or an ellipse, which we have already used so far. Okay, we have used in 2D the equation of a circle and an ellipse, and those points lie on a plane. But a curve could exist in 3D as well. Okay, the curve could exist in 3D as well. In fact, the circle could exist in 3D. the points on a circle lie in a plane. It's a two dimensional distribution of points, but if that plane can be visualized to lie anywhere on a 3D, either a plane or a circle, then we also have a curve in 3D. So we know those special functional forms of those curves which produces a circle or an ellipse, and we will see some more such special forms of curves today to start with, for you to get used to these expressions of curves for, say, let us say parabola or a hyperbola, okay, or an ellipse or a circle. Okay. Of course, circle is a special case of an ellipse. So, if you have equations of parabola, hyperbola and ellipse in mind, you can actually generate various types of curves by varying these parameters of 3 different curves. And all these 3 different curves again are special types derived from one particular generalized curve representations or curves of what are called the conic sections. Conic sections. Okay. Let us introduce the word conic sections in this lecture today. A conic section is obtained by what? Okay. The word cone is present. So, you take a cone and you can obtain a conic section. Can you guess how? Yes, you take a cone and intersect that cone with a plane. Okay. Take a planar surface and intersect the cone. Now, the relative locations of the cone and the plane will dictate what is the intersection you obtain. Okay, but whatever intersection you obtain, you will get a curve. The intersection of two surfaces will be a curve. Okay. In 2D, intersection of two lines gives a point. In 3D, the intersection of two surfaces yield a curve. That curve could be in 3D, or the distribution of these points on the curve could be on a 2-dimensional plane. That is already, it should be in a plane, because you are using a 2-dimensional plane to chop off, let us say, a cone, and the resultant intersection of the contour which you get, let us say, of the conical surface, and that which intersects the planar surface results in a conic section. So, that is the idea of a conic section, intersection of a cone with a planar surface. Okay. So, which we will see. So, we will look into first a second degree implicit representation of a curve and then move on to conic sections. And I must inform you a priori that we are, after quite a few series of lectures as we discuss various types of algorithms on computer graphics, we are back to mathematics again. Okay. If you remember, of course, when we talked of 2-dimensional transformations, 3-dimensional transformations, 3-dimensional viewing, we had a lot of equations, mainly true with matrix manipulations. Of course, the same will come here, but we will probably come with second degree or third degree equations here. And I request you that you please copy these equations and then try to derive some of these derivations I have used in the slide. Some of them I have left it open for you as an exercise to try out. Please practice these equations yourself, draw these figures which will come on these slides yourself. You need to practice these equations, otherwise you will not be able to master both the concepts of visualizations of these curves, and of course, then surfaces will come at the end of this remaining series of lectures here. And you must practice these equations to get a strong feeling and control over this set of representations of curves. Okay. So, let us look back into the slide. The second degree implicit representation is often given by this expression. You see, this is a second degree equation because you have square terms both in x and y, and of course, you have a binomial term here x y, and you look at the coefficients, you have 7 of them, a, b, c, d, e and f. Okay. And this is an implicit representation of a curve, something similar to f x y is equal to 0 with 7 parameters. The only point which you should start thinking is there is a factor 2 here, which is added to b, d and e. I could have written this expression in the form of x square plus bxy and then cy square dx plus ey plus f is equal to 0. That means just throw out the factor 2, and it occurs in 3 of those 7 terms. Okay. And you keep guessing why. Okay. The answer will be not in this slide, but after a few slides in this lecture today towards the end, and we will see why this factor 2 is. But also you can represent a second degree implicit form without this factor 2. Nobody stops you from doing that. Okay. So, but there is a reason, mathematical reason and a logical reason also later on we will see why this factor 2 is used. Okay. So, you can keep guessing why there is a factor 2 used in along with the coefficient b, d and e only, but not with a, c and f. Okay. So, this form of the expression with the coefficients provide a wide variety of 2D curve forms which are called the conic sections. We talked about this conic section just now, and this is the mathematical expression of a conic section given on the top of this slide, and this form of the expression with the coefficient. That means, if we keep varying these coefficients, that is A, B, C, D, E and F. So, there are 7 of them, A, B, C, D, E, F, I am sorry 6 of them, 6 of these coefficients are present in this second degree implicit form, and you keep varying these coefficients in the implicit representation, you will get various types and forms of curves. Okay. In of course, 2 dimensional, because you are talking of x and y. So, in a 2 dimensional plane or 2 dimensional axis system, you will have various types of curve, and they all fall under the broad generalized category of what are called the conic sections. So, if you look back, that is what we will call as the conic sections, and we know we have just discussed some time back what do you mean by conic sections here. So, that is the implicit form, and they are called the conic sections. So, let us look at some special forms of conic sections. I did mention some time back that the 3 special cases of conic sections are parabola, hyperbola and ellipse. So, we will discuss 3 of these, and we will discuss 3 special cases, not with respect to those 6 parameters of the second degree conic which we just discussed. Now, we will bring that later on. So, do not confuse the coefficients A, B, A to F, 6 of those which we discussed in the previous slide for the generalized second degree implicit representation for a conic. That was the form, all right, but we will see when those special forms and what are the ranges of values. If you give to those 6 parameters, you will have special curves like the parabola, hyperbola and the ellipse. But we will look into the geometrical class of equations of parabola, ellipse and hyperbola. These are again given in any books of fundamental books on geometry and computer graphics. So, we will look into those expressions, and the parameters used now to describe these 3 different curves are not related right now. Do not relate these with the parameters which we have discussed. So, come back to the parabola. So, this A is different from the A which we discussed earlier. I repeat, this A has no relation with this parameter A in the second degree implicit representation. This is just a generalized form of a conic. So, let us first discuss the special forms. This A is called the focus of the parabola. We will come into the figure of the parabola later on, but we will just see first these 3 special forms of these special types of conic sections, or special class of conic sections also. I can say parabola is an expression y square equal 4x, you all know that, and A must be a positive number, otherwise y will be imaginary, we will know that, and so focus of the parabola is a comma 0. We introduce the term directrix here, which is given as minus a. We will define this later on using the figure. So, it is a point x equals minus a. It is a point on the x axis, or you can visualize this directrix to be a vertical line x equal to minus a. X equal to minus a will be a vertical line which is parallel to y axis, and it will be on the negative towards the negative x axis. So, that is called the directrix. Okay, we will see that in the figure. So, that is the directrix. So, we know what is the focus and also the directrix, they are symmetrical. Remember, focus is a point, but directrix is a line. You also define the term eccentricity in this context, which is a very important property of all these special conics, E, which is equal to 1 in the case of a parabola. We will see that eccentricity E will not be equal to 1 in the case of hyperbola or ellipse. In the parabola, it is equal to 1. We will define what is eccentricity. It is the ratio of 2 different distances. You will see what is this eccentricity term. These are different forms of writing the parabola also. This is a parametric form of writing the parabola. So, with the parameter A given here, x equals a t square, t is the parametric form, a is the coefficient of the parabola, and so if you substitute these two in equals onto y square equals 4x, you will see this is satisfied. It can be also represented in another parametric form, trigonometric form, using this particular expression x and y, tan square phi. Of course, phi has to be within certain range, and this is also an expression of the parabola. We will see the other forms and then look into the figure for the case of a parabola. This is the equation of a hyperbola. Okay, this is the equation of a hyperbola. We will see the difference between the two and then look into the figure also. So, there are two parameters in the expression of the hyperbola, a and b. Okay, as given here, we had only a coefficient a for the parabola. Now, there are two coefficients a and b for the hyperbola. This is the expression, and it could be also written in an expression form like this in terms of eccentricity. Okay, in the form of eccentricity, it could be also written in this corresponding form where eccentricity is more than 1. Okay. Eccentricity is more than 1. The relation between A and B is given in terms of this eccentricity here, where E is more than 1. Okay. So, the coefficients A and B are related using this expression. There are two focus. So, we have a foci for an hyperbola at plus and minus A multiplied by E. At plus and minus A multiplied by E, we have the focus of the hyperbola, and the directrix is given by again lines, vertical lines, but there are again two of them. Remember, in the case of parabola we have x equals minus a, but in the case of hyperbola we have x equals to plus and minus a by e. So, you can use the same expression since e is equal to 1. So, it does not matter, I can simply write minus a here in the case of a parabola, because a by e with e equals 1 will give you minus a. Okay. So, directrix is basically plus and minus a by e in the case of hyperbola, and the focus will be plus and minus a 0. Okay. So, this is the parametric form for the hyperbola, as you had this in the case of a parabola a t square and 2 a t. As the parametric form for a parabola, we have this, or even this, let us say for the parabola in terms of tan of phi, we have in terms of the secant, which is 1 by cosine term, and the tangent of t. So, t being the parameter a and b being coefficients of the parabola. Let us say I will use, you can use parameters a and b, but I will use coefficients a and b, and t being the parametric form, the parameter of the parametric form of the expression. T varies between this range, okay, minus pi by 2 to plus pi by 2. A special case when the eccentricity E, which is more than 1 as given in the case of a hyperbola, becomes equal to root 2, then it becomes a rectangular hyperbola. E is equal to root 2, okay, in the case of rectangular hyperbola, and x and y are given by in the parametric form also as c multiplied by t or c by t. C is an arbitrary constant, then this hyperbola becomes a rectangular hyperbola. We will see this special case when we look into the figure of what is a rectangular hyperbola with respect to a normal hyperbola given by this expression here or the parametric form given here. So, I hope the concept of focus, directrix and eccentricity is getting clear. Of course, we have to identify what is the expression of the eccentricity here, which is more than 1. We look into the third form, which is an ellipse, as given here. The nature is actually almost similar to the case of an hyperbola, where we have the minus sign replaced by the plus. That is the change. So, we have the ellipse, and of course, the special condition is that a is greater than or equal to b, and b, and that should be always positive. A and b are always positive values, and the relation between a square and b square is almost similar, since now the eccentricity in this case for an ellipse, unlike the hyperbola where we had the eccentricity more than 1, it is now less than 1. It is a fractional number lying between 0 and 1. So, these are very interesting information where we have in the case of a parabola the e, we will use the word the variable e mentioning or specifying the eccentricity of this special type of conic section. So, e is equal to 1 in the case of a parabola, it is more than 1 in the case of a hyperbola, it is between 0 and 1 in the case of a ellipse. Ellipse fractional number 0 to 1, when it is equal to 1 we have a parabola, and if it is more than 1 it is a hyperbola. So, these are the three ranges. It is never negative, because the eccentricity is the ratio of two distances. We will define that term later on using a figure. Right now we will go ahead and finish the differences in terms of trying to look at the focus, eccentricity E, and directrix for these three curves. So, the focus is plus and minus a multiplied by e in the case of ellipse, as it was a by e in the case of a hyperbola, it was only minus a. In the case of a parabola, it is plus and minus a e. Okay, and of course, it is on the x axis. So, its directrix is here, sorry, focus is here, focus is a, it is a e plus and minus a e in the hyperbola, and plus and minus, it is the same in the case of ellipse and hyperbola. Directrix is a by e, directrix is a by e, as the same as the hyperbola. Directrix was a, since a is equal to 1, the formula of directrix is actually the same. So, these are vertical lines at plus and minus a by e. In the case of a parabola, it is only at minus e. This is the parametric form for the ellipse. So, cosine t and sin t, you can see that from ellipse it can degenerate very easily to a circle when a is equal to b, okay, and the t is within the range minus pi to plus pi. So, you have a full period for the ellipse which comes back. Okay. So, let us look at the figures now for the parabola and the hyperbola first. So, starting with the parabola, as I was talking about, the focus was at f, which is a comma 0. So, this distance is a. This is a point P, any point on the curve, say P x comma y, it could be anywhere on the curve, and the vertical dotted line is the directrix which is at x equals minus a. You look back, if you remember, the directrix is at minus a as given here for the case of a parabola. So, if you look forward for the parabola, the directrix is at minus a, okay, and this is the origin O. This is a point M, which is the perpendicular dropped from the point P on the directrix line on the directrix. If you drop a perpendicular line from P that or project the point P on the directrix, you get the projection of P as M on the directrix line. Okay. So, the eccentricity term, which is defined as E is equal to 1 here, of course, it is not very clear with respect to this figure. I must admit here that these most of these curves are not purely computer simulated. Some of them will be computer simulated, but I have tried to draw them by a hand sketch. So, some of these are qualitatively looking very good, but may not be quantitatively accurate. So, I must inform you this. So, for a parabola, the eccentricity is defined by the ratio of this distance, that is between P to F and P to M. I repeat, from P f to P m, that the ratio of the distance of a point on the curve to the focus divided by the distance of the point from the on a curve to the directrix. So, the ratio of this distance, these two distances is the eccentricity E, and since we are talking of a ratio and distance is always a positive value. So, the ratio also will be a positive number, it will never be negative. Of course, it could be less than 1, it could be equal to 1, it could be more than 1, and based on these three conditions we have three different curves. As for example, in the case of a parabola, these two ratios, these two distances are same, and hence the eccentricity E is equal to 1. So, E is equal to 1 in the case of a parabola, we have seen it is more than 1 in the case of a hyperbola. Ellipse, it is less than 1, but greater than 0. So, it is a fractional number. So, remember these three ranges of the values of E. I hope you have noted down very carefully these three terms from the previous slide itself, and remember the eccentricity we have just defined now with this help of this figure. It is going to be, the definition is going to be the same. It is the ratio of the distance of the point on the curve to the focus divided by the distance of the point with the from the directrix. So, that is the definition of eccentricity of the parabola here, and this is the case for a hyperbola. Okay. And we have two directrix as given earlier at plus and minus a, two of these vertical dashed or dotted lines at x equals a by e here and x equals minus a by e here. This is the origin, and this is the point P again on the curve on the hyperbola. You drop the perpendicular on to the M. So, if you take a point P here on the negative x axis, you can drop and you will get another point M here. So, this is the distance which is be more than 1 here, that is P to F divided by P to M. So, that is the eccentricity here. The focus is now A e, okay, because since E was equal to 1. So, it was a comma 0, now it is a e comma 0, and a is more than 1, we know that. So, this is the case of a hyperbola. So, this is how an hyperbola qualitatively we will look at. I must again admit that this is not a computer simulated one, but one can easily do that using any simulation toolbox. You can use Simulink or MATLAB toolbox or any other thing to or any other plot command to generate points on for a hyperbola, parabola, and ellipse and plot that. Okay. So, this is the qualitatively the curves will look like this. Let us look into the last one, which is for the case of an ellipse. It has two focus here, like the case of a hyperbola. So, it is at a comma 0 and minus a comma 0. So, these are the two focus of the ellipse here, okay. And this is the point P x y 0. Remember the definition of E term, that is the ratio here will be such that this intersection is at a comma 0 here for the ellipse, it is b comma 0, 0 comma b at this point and a comma 0 at this point, and the ratio of the distance will be less than 1, but more than 0. So, this is the ratio of this by this distance P to F and P to M here, you will mark this point as M, and P to F and P to M will be between 0 and 1. It is a fractional number. So, this is the case of an ellipse. We will go back and compare this figure with the case of a parabola and hyperbola again. So, this is what you have for a parabola and hyperbola, focus A comma 0 or A comma 0, directrix plus and minus A by E. The same concept holds good here. There are two directrix for an ellipse, the two focus A comma 0. Parabola, of course, you have only one directrix and one focal point, and the eccentricity is defined by the ratio of these two distances of the point from the curve to the focus and projection of the point on the directrix. So, this is what we have as the three special curves of as conic sections under the category of conic section, three special classes of curves as parabola, hyperbola and ellipse, where the difference is mainly in the eccentricity term here which distinguishes. But of course, we have seen in the previous slides also that the expressions also do vary in terms of the Cartesian coordinate form or the parametric form of the expressions of an ellipse, hyperbola or parabola. So, let us look back into this slide to compare the three different special classes of conics, the parabola, ellipse and hyperbola once again, and we will look back into this slide to find out the difference in both the Cartesian coordinate form, then the focus which is AE comma 0, E is equal to 1 in the case of a parabola, E is greater than 1 in the hyperbola, E is between 0 to 1, it is a fraction in the case of an ellipse. The directrix is at AE, okay, minus AE here, single directrix in the parabola, two directrixes here AE plus minus A by E, the directrix is same expression in the case of a hyperbola and ellipse, and of course, the parametric form here. You can either use any of these or this in the case of an hyperbola using a trigonometric form, 1 by cosine and a tangent, and a cosine and a sine in the case of an ellipse. Okay. So, that is what the three expressions for the conics are. Look back at the figure, these are the figures again for the parabola and hyperbola, the directrix, the focus are the main area of interest here. We should know how to compute the eccentricity by the ratio of these two distances, and the case of an ellipse as well here. Okay. So, once we have seen these three forms of the special class of conic sections, we will move forward to talk of the general form of a conics once again. But I will probably give you an home assignment right now to derive the polar coordinate of the equation of a conic. The polar equation of a conic, take this as a home assignment. If you look back into this slide, I will give you the answer, try to derive this and take it as a home assignment. The polar equation of a conic given in this particular form or theta form, where L is the distance of eccentricity E multiplied by the distance between the points F and D. Focal point F, F is the focal point, D is the directrix, D is a point on the x axis, so you know that, and so F comma D distance is what is L, and so this is the result which I want you to derive, L divided by 1 plus E cos theta. I will give you a hint to derive this expression. Okay. Once you pick up this hint and follow it, it will be easy, otherwise you cannot easily derive this from the Cartesian coordinate form. Assume the focus to be at the origin, assume the focus to be at the origin, and that will help you to derive the expression of this polar equation of a conic in Cartesian coordinate form. So, coming back to the second degree general expression of a second degree implicit representation of a curve, and if this conic section passes through the origin, then we of course the parameter f goes down to 0. Remember, this a and b has nothing to do with the a b which we discussed as parameters for our ellipse, parabola or hyperbola. These are the 6 parameters of the second degree generalized expression of a conic, and we now we will discover, if you have not understood why we need these factor 2 in 3 of these 6 conics. But you can easily visualize that if this conic passes through the origin, okay, then f is equal to 0, because if you substitute x and y is equal to 0 onto this expression, you will easily derive that the factor f or the coefficient or parameter f should be equal to 0. Assuming one of the parameters to be a constant, say c is equal to 1, okay, or f is equal to 1, whatever, but of course, f can be also visualized to be 0 either by assuming the conic section to pass to 0, or we can move the curve such that the curve passes to the origin, or the origin can be moved to a point on the curve. We have done this cases when we were drawing lines, circles and ellipses using Bressenham's integer algorithm. So, moving the origin to the point on the curve or bringing back the curve to the origin does not make a big difference. So, you can always do that and normalize the parameters and shift the curve back. We know the translational functional form. So, assuming one of the parameters to be a constant, we are actually will be having 5 coefficients left, and those have to be derived or obtained using 5 geometric conditions. So, either one of these c and f can be assumed to be a constant or known, okay, either f to be equal to 0 or f could be mean is equal to 1 or c is equal to 1. You can actually do this by dividing this entire expression by any one of these parameters. Okay, try to do that. Take this entire expression and divide this by either c or f. You will get rid of one of these parameters very easily. So, you will be left with 5 out of the 6 parameters. So, we are talking of these 5 coefficients. So, there are various ways by which this 6 can be reduced to 5. Okay, one of them is assume the curve to be passing to the origin. So, f is equal to 0. The other thing could be that you can take one of these to be constant, c or f to be equal to 1. The third way of visualizing this is divide this entire expression by any one of these coefficients, again c or f. So, you will be remaining with, you will be left with only the remaining 5 coefficients out of the 6, and looking back to the slide. So, these remaining 5 coefficients out of the 6 may be obtained using 5 different geometric conditions, and the boundary conditions can be obtained by these special conditions of boundaries, where we talk of 2 endpoints. So, we assume the 2 endpoints of a curved unknown x1 y1, the curve is travelling from a point x1 y1 to a point x2 y2. This had happened in the case of a line. Okay, when we drew a line using Bressenham's, also the line moved from a point x1 y1 to a point x2 y2. Of course, in the case of a ellipse or circle which we drew with Bressenham's, of course, we knew where the curve was starting from, a comma 0, we were moving in the second octant or first quadrant. In the case of an ellipse or circle, and using symmetry we generated the point. So, we know where the point, the starting point we know, and in most cases in the case of a curve we know, we assumed the finishing point to be known, otherwise the curve cannot be defined. So, the 2 endpoints are the boundary, first 2 boundary conditions. The 2 endpoints are known as the boundary conditions, and we also assume that the slope of the curves at these 2 endpoints are also known. So, not only we know where the curve starts and where the curve finishes, okay, it could be in any form, okay, but we know how the curve starts and how the curve finishes. Like in the case of an ellipse, hyperbola, parabola or circle, if we take a part of those curves and say this is our arc of our interest, we will not only know the starting point and the finishing point of a circle, ellipse, parabola, hyperbola, whatever curve we are talking about, but we also know how the curve starts and how the curve finishes. When I talk of this term how, I mean the derivative or the slope, okay, or the tangent to that curve at those starting and finishing points is also known. I repeat, I not only know the starting and the finishing point of the curve, but I also know the nature by which the curve leaves the starting point and finishes the at the end point. That means, the tangent to that curve at the starting and finishing point is known, or the slope of the curve or the derivative of this curve is known. It is something similar to, if I try to give an analogy in the physical world, we know the trajectory by which an aircraft will take off and the trajectory by which the aircraft will also land in an airport. That is pretty well defined, and all the aircraft which are flying in the world have to follow certain trajectories of descent in terms of its slope or derivative. Of course, it is not a pure curve, sometimes it could descend in a linear form, but at the end it could have a slow moving curve form and tangentially touch the point at the airstrip where it lands, and of course, it must also take off in a particular manner from the airstrip at the starting point. So, we have a starting and a finishing point, and we also know the derivative slope or the tangent to those curves at those 2 points. So, those are the first 4, 2 plus 2, 4 boundary conditions, and the one more boundary condition what we can visualize is we will assume an intermediate point. So, that is why we have the 5 geometric conditions to obtain the 5 different coefficients of this generalized conic, and we know how the 6 parameters or 6 coefficients have been reduced to 5 coefficients, and we now use 5 geometric conditions to obtain these 5 different coefficients of the generalized conic. What are those 5 boundary conditions? Please try to recollect. 2 are the 2 endpoints, coordinates of these 2 point points x1 y1 x2 y2. In 2D you can visualize this curve in 3D also, x1 y1 z1 to x2 y2 z2, the curve could be in 3D, that is also possible. So, we know those 2 coordinates of the 2 endpoints or the finished starting point and the finishing point of the curve. We know the slope of the tangent, that is how the curve will start and finish. Okay, the slope of the derivative, say the curve is coming out like this. So, that is a tangent to the curve, and the way it finishes at the end point. So, we can also define this, we will come up with that figure illustrating the slope or the derivative or the tangent to that curve at the end point and finishing point. So, 2 end point coordinates and 2 of the derivatives at the slope and end point. So, 4 of them, and 5th point is obtained by an intermediate point in between, because we not only should know where it starts, where it finishes, but we should know some point in between where it is going through traversing. So, if we change any one of these 5 geometric conditions, either the starting point or the finishing point, or any one of these 2 tangents at the start and the finish, or even the intermediate point, if you vary, what will happen? The curve will change. Okay. The nature by which the curve appears or looks like will change, and in mathematical terms the coefficients will vary. The coefficients which define this curve in terms of this 5 or 6 also will vary. So, these are the, look back into the slide. So, this is the general way by which these coefficients are obtained. So, there are 6, from this we reduce to 5 by allowing the origin to be at the conic, or the conic to be at the origin, or assuming one of the parameters to be equal to be a constant, and we are left over, or we have 5 of these coefficients which may be obtained using 5 of these geometric conditions, 2 endpoints, 2 slope of the curves at the endpoints, or the tangents or the derivatives of the curves at the 2 endpoints, and 1 intermediate point. So, I hope this is clear, and when we look forward we will see special forms of these conics also. We have to find when these A, B, C, D, E, F result in these 3 different special type of conic sections, like the ellipse, parabola, hyperbola, and of course, when you know an ellipse you can also say circle under that category. Generalized conic, if you look back, that is the expression. So, we have still not discovered or found out why these 2 is necessary. So, we will talk of that right now. We will reorganize this expression of the generalized conic in a matrix form in this nature. Okay. In this form, we reorganize this expression in the form x s x transpose is equal to 0, where x s is a symmetric matrix 3 cross 3. X is given by this particular form, since it is a 2D x y 1 vector. So, it is x is nothing but a homogeneous representation of a point in 2D, that is x here, and the S is a symmetric matrix with the coefficients A, B, C, D, E, F obtained from this quadratic expression here, and is plugged into this matrix 3 cross 3. So, you can see, I leave this as an exercise for you to visualize that if you break open this expression, you will get this quadratic form. Okay. So, you can almost visualize that if you multiply these 3 matrices, you will get this one particular expression. Okay. Okay. You can take this as a home exercise, or you can solve this when I am as the lecture proceeds, to visualize that how this matrix form of the expression could be either derived from the second degree, or the second degree expression could be obtained from the matrix form. Now, if you carefully look back, the S matrix which is given here is a symmetric matrix. There are 2 of these terms, B, D and E. I repeat, 2 B's, 2 of these D's and 2 of these E's. And this has to be there because S is a symmetric matrix, A, C, F are the diagonal terms. So, the non-diagonal terms or the off-diagonal terms in this symmetric matrix must duplicate itself to give the symmetric nature of the matrix, and if that is so, you require 2 of these off-diagonal terms, which are B, D and E, and hence that is the reason why we use that factor 2 in that quadratic form. That is the answer to my question which I put at the beginning of the class today, why these 2 could be used. You may not use 2, nobody forces you to use 2, but if you do not use 2, you can still write the expression second degree of the generalized conic in this matrix form, but what will happen, you can imagine. What will happen? That symmetric matrix, the off diagonal terms will have to now have a divide by 2 term. So, we will have a b by 2, d by 2 and e by 2 in those off diagonal terms. So, to avoid that divide by 2 term in the matrix or the off diagonal terms of the symmetric matrix X, to keep the diagonal terms as it is without a divide by 2 term, we add the factor 2 in the second degree expression for the generalized conic 2b, 2d and 2e to ensure that you do not have a divide by 2 term in the symmetric matrix. As I look back, see, if you eliminate this 2 here, that means do not use 2 in these 3 terms, that means use just bxy, dx and ey, you can still write in this form, reorganize in this form and come up with a symmetric matrix again, but you will have a b by 2 at these 2 places, you will have a d by 2 in these 2 and in this you will have an e by 2. So, to avoid that divide by 2 factor in the off diagonal terms of the symmetric matrix S, you introduce the factor 2 here. So, that is the answer to my question. Okay, I am not sure whether all of you got this answer before I gave the solution. I mean the reason behind, it is not a solution, it is a reason behind using the factor 2 here. Okay. So, this is the expression which is used for the generalized conics in matrix form. You can also write this generalized conic expression in this form, particular x, a, g x and f. I leave this as an exercise for you, where this f is the same as this, g x will be involved with d and e, and a will not, a will have only the matrix a, c and f. It will be a diagonal matrix in fact. A, let me visualize. What will happen is, now it will be again a symmetric matrix, because you will have the a, c, f will be 0, you will not have this factor f because it is coming out. So, I leave this again as a home exercise to write the expression of a given g as your e, d and e terms will go into the matrix G, the f is this term f. So, if that is so, what is going to be your a matrix 3 by 3 when S is given here? If S is given as this, I have already given some part of the solution where f will vanish, d and e will not remain, and so it will be the ABC terms will remain in fact, and you will have 0 0 and you may have a singularity 1 term here. Okay. So, please try to write this matrix A. It will be again a symmetric matrix, but it will not be in the form as given by S here. Okay. So, there are 2 different ways by which we can write the generalized conic second degree implicit representation of a conic in the form of a matrix, either x a x s transpose equal to 0, otherwise x a x transpose plus g x plus f is equal to 0. Look back, either you can write in this form or you can write in this form, but you will stick to this form because it looks highly compact and quite easy to handle. Okay, special conditions when the second degree generalized conic becomes a parabola. Out of those 6 parameters, when b square equals AC, that equation, which is that equation which you are talking about? We are talking about this equation. The generalized second degree implicit representation of a conic becomes a parabola when b square equals AC. That is very interesting, it becomes a parabola. If b square is less than AC, then the equation represents an ellipse, and you can almost guess that if b square is greater than AC, the equation represents a hyperbola. So, these are the special conditions of the second degree conic. So, relation between b, a and c, or b square and AC dictates which of these 3 forms it is going to take. So, the linear term, that is the d, e and f, does not have a significant role to play with. In fact, if you go back and look into this expression here, you can visualize that if I switch off a, b and c, that is put a is equal to 0, b is equal to 0 and c also equal to 0, you will be left with this term in the generalized conic. What will this expression give you? Any guess? When ABC is equal to 0, this expression will give you a straight line. It is a linear form. It is a linear form of the generalized expression of the conic. So, that is the linear term. So, D and E and F are responsible for the linear part of the expressions. The second degree terms a, b and c are what are going to dictate what is going to be the form of your conic. Okay. So, bring this back, b square equals ac is a parabola, second degree term relations again, b square less than ac is an ellipse, b square more than ac is a hyperbola. Okay. We move on to second degree space curves in 3D, which can be represented by explicit non-parametric representation as this, where x is equal to x, y is equals fx and g of x. It could be any functional form f and g, second degree or third degree or even linear forms of. You can almost visualize that this will represent a plane if f and g are or a line or a plane if it is a linear form f and g. You can have non-parametric implicit form f x y z equals 0, g x y z equal to 0, that is also possible. This is an interesting case, non-parametric implicit representation f x y z or f x y equals 0, g x y equal to 0 in 2D, or f x y z equals 0 and g x y equal to 0 in 3D. Now, if these f x y z and g x y z are linear expressions of x y z, you can visualize that these two are going to be planes. We have seen this equation of a plane x plus by plus cz plus d is equal to 0. So, if f x, so this functional form f and g, if they are linear, they will represent a plane, or they represent two different planes f and g, and two different planes will intersect to form a, you can know that it forms a line. So, a straight line can be represented in parametric form, or it can be represented in an implicit form as intersections of two planes. Two lines intersect to form a point in 2D. I talked of this earlier on, and now two planes in 3D intersect to form a line in 3D. In 3D, correct? If these two functional forms represents a nonlinear surface, it could be a cone, it could be a cylinder, it could be a sphere, or any other arbitrary surface depending upon the coefficients. 6 of those we have seen in the x y, but you can have more of those when you have 3 variables x y z. So, if you have two arbitrary surfaces, non-planar curved surfaces in 3D, intersections of those will produce not a line, it will produce a curve. A typical example is, try to visualize an intersection between a sphere and a cone. Okay, assume a sphere and a cone in between. So, intersect those two surfaces, you will come up with a conic section also, but it will be any general curve depending upon the relative positions of the sphere and the cone. We talked about a conic section between the intersection of a cone and a plane. That intersection gives you a contour which is called a conic section. But two different quadratic surfaces or second degree or curved surfaces, as they are called popularly, they will intersect to form a curve. Okay, you can visualize any sphere, ellipse, ellipsoids, or even cylinders and cones intersect, any two of these will intersect to form a curve. So, that is what is the representation of a curve in implicit, as these two equations, when they are simultaneously satisfied, will have a curve in 3D. That is what we are talking about. Intersection of the above two surfaces represents a curve. Examples. Okay, this is the parametric form, x t cube t square and t. We are talking about a non-parametric representation, explicit non-parametric representation or parametric representation in the form of t cube explicit, where of course, in this case you can put x equals x, y equals x square and z equals x cube can be visualized as a parametric form. Explicit parametric form is this. Okay. And parametric space curve can be represented as xt, ft and zt with terms of t, and examples I will give as the curve on the seam of a baseball. Okay. If you see x, y, z and the theta is the one which is varying in this particular range, there are two other parameters, lambda, mu, a and b. A and b are the parameters. You can define lambda and mu in terms of another parameter d, theta and c. This is highly complex. I will tell you what this curve of a base of a on the seam of a baseball means. Now, that is not a popular game in our country, but it is very popular in the West. I talk of the curve on the seam of a baseball, which is thrown at a very fast speed. Okay, the tennis ball which is used to play lawn tennis also has a similar structure. Okay, so, the curve on the base of a symbol, the curve on the curve which is the seam of the baseball will have a structure which will be on the surface of a sphere, all right, but it is quite curved, and that can be also represented in the parametric form, and it is not very easy. I ask you to refer into book. I do not have the example of that particular curve right now in the presentation, but you can look into book by the Rogers and Adams and other books which talks of these illustration of the curve on the base of a seam of the baseball, which will be represented in x, y and z in this particular form, lambda and mu in this again a function. So, a, b, c and d are the parameters of the curve in this case, and are the coefficients, and theta varies in this particular range 2 pi t, where t varies between 0 to 1. So, if you vary t from 0 to 1, theta will vary from 0 to 2 pi, and you are basically tracing the curve on the seam of the baseball. That is very interesting complex formulation, but interesting. Vary t from 0 to 1, theta varies from 0 to 2 pi, and you are tracing the curve on. Okay. Helix is a very interesting example. This is something like the polar coordinate form or cos theta type, but we use t which varies from minus infinity to plus infinity, and as you vary that, you can see cosine and sine. This is a circle or an ellipse. It is basically a circle. I can put R1 or not to make it an elliptical structure, but helix has a circular base, and the z varies linearly. P is not equal to 0. It is a positive number or negative number. So, we are talking of a helix like a spring type of structure. So, when you vary that, xy follows a circular pattern, but z varies. So, when you vary t, xy varies in a two dimensional plane like a circle, and z varies linearly. It goes up or it could go down based on a positive or negative value of z. A positive or negative value of b will dictate whether the z values are going up circularly or coming down. So, you can visualize this to be a very larger spring structure going up or down. Okay. We will introduce the parametric cubic curves before we wind up the lecture today, which will in fact open up a wide scope of discussion of various curves, where we talk of x t, y t, z t is as cubic curves, parametric cubic curves. So, each of these expressions are we have a linear second degree and third degree term. So, it is a cubic expression of t as a parameter, and a, b, c, d are the 4 parameters in x, y and z. So, the subscripts indicate the parameters in the x, y and z domain, and you can rewrite this expression or put them together into matrix form as q of t, indicating the parametric cubic curve expression is x t, y t, z t, as t multiplied by c, where t is given as this particular matrix. It is a vector of the parameters t cube, t square, t and 1, and c as this particular matrix. Okay. So, this is what you can write as your parametric cubic curve expression. Okay. Parametric cubic curve expression is what you can write in this particular form. You can actually transform it in a slightly different form. If you look back, if you go forward, keep this in mind. If you have copied t and c, it is very easy. As you can see, this expression ax, ay, az to dx, dy, dz form this parametric matrix C. You go ahead and in general we write qt, which is same as x t, y t, z d in the form of t, m and g. So, you break C into two parts, m and g. T remains the same, m and g is a matrix Mij, a 4 cross 4 matrix, and g is a 4 cross 1 matrix G, where m is a 4 cross 4 basis vector matrix M, and G is a 4 element column vector or a geometric constant called the geometric vector. So, M is called a basis matrix M, and G is called a vector of geometric constants, or it is called a geometric vector. Okay. This curve is now hence a weighted sum of the elements of the geometric matrix or the geometric vector. So, the weights are given by this basis, and G is what controls the geometry of the curve. The weights are each cubic polynomials of t. Okay. The weights can be visualized as t multiplied by m is called the basis matrix or the and are called the blending functions B. So, the various ways by which these curves are represented, t multiplied by m gives a matrix B, which is also called the blending function. So, these blending functions will act on the geometric vector given by G's. You must write these expressions yourself to get control of this. So, there are various terms we introduced in the class today. We talked of a basis matrix, we talked of a geometric vector G, and we talked about a weighted sum of these elements, and then we also called of a blending function, B, which is again if you look back, B is the product of t multiplied by m, t multiplied, that is a blending function which blends on the geometric vector G. So, B multiplied by G gives you a curved shape. So, depending upon various types of these basis vector, geometric vector and blending functions, you can have different types of cubic curves. Okay. Cubic parametric cubic curves of this parameter t is one which will hold the parameter, and you vary m and g or the blending function B, which is a product of m and g, to get various types of parametric curves, okay, in space curves or in 3D. We will start from here on in the next class, where we will have extensions of these parametric curves in different forms, and we will see that we come up with cubic splines. This lends itself to curves, special class of curves called Bezier curves, which are used to based on certain geometry. These curves will take different shapes, cubic splines, Bezier curves, and also a combination of these which leads into what are called the B splines. So, these are the curves, and of course, toward the last lecture we will talk about various, towards the end of the last lecture we will talk about various types of surfaces which are extensions of curves in 3D. Thank you very much. We will stop here.